Good morning. Today we're going to be talking about transfer functions. By definition, the transfer function of a linear time invariant system is the z-transform of the impulse response. So if we have h of n, or if we call the impulse response h of n, take the z-transform, what we get is the transfer function h of z. This is useful to us when we want to calculate the output of systems. And we know that the output of linear time invariant system is the convolution of the input with the impulse response. Now, we can do the convolution as we did before, but it turns out in general it's easier to do it with z-transforms. So if we take the z-transform of this equation, y of n becomes y of z, x of n becomes x of z, h of n becomes h of z, and we know that a convolution in time is a multiplication for the z-transform. So this would be our equation, right? The output is just a multiplication of x times h. Now this is useful, as I mentioned, when we want to calculate outputs of systems. So let's do a couple of examples. In this problem, they're going to give us the impulse response, they're going to give us the input, and they want us to calculate the output of the system. Now in this problem, everything is given in time. We're given h of n and x of n. Now we don't want to convolve this to get y. We're going to take the z-transforms and multiply them. So we take the z-transform of h of n, we get h of z. Now both of these are relatively easy. We've done this before, right? This has the form a to the n mu n. So we can write the transforms directly with their regions of convergence, right? For h of n, the region of convergence is z greater than 0.8. For x of n, it's magnitude of z greater than 0.3. So again, the output is just the multiplication of the input with h of z. We multiply these functions together, and this is what we get. Now, when we multiply these two things together, in general, the region of convergence is the intersection of the regions of convergence of each term. So we take z greater than 0.8, z greater than 0.3, and the intersection is z greater than 0.8. Now we take the inverse z-transform, as we have done numerous times, right? We do a partial fraction expansion. We get a0, a1, and a2. No great mystery here. Let me leave it here for a couple seconds so you can look at. Pause. The best thing, of course, would be to pause the video. Make sure you can calculate these. Make sure they're correct. And let's go on. Now this would be our partial fraction expansion. And we can take the inverse of each term. We have minus 0.6, so that's just a constant. We're going to have 0.3 to the n times mu to the n because the region of convergence is greater than 0.3. And here we have 1.6, and again we have 0.8 to the n times mu to the n, since the region of convergence is greater than 0.8. So in general, if they give us x of n and they give us h of n, we can calculate the output with z-transforms. In one earlier video, I had talked about the general use of the z-transform, and you even wrote some difference equation describing a system. In this case, we're not going to that extreme, but we can use it to get the output of the system, right? If we know the input, if we know the impulse response, we can get the output. Now, how do we get the transfer function? Well, there are a number of ways. If we know h of n, we can always take the z-transform of h of n. But how about if we don't know h of n? Sometimes what we know is the difference equation. Now, instead of taking the difference equation, finding h of n, and then doing the z-transform, we can actually go from the difference equation directly to the transfer function. And let's see how we can do that. Let's say we have the difference equation, and let's say we can write it like this. So we could write it as a summation, or we could write it out in each term, right? So we have n plus 1 terms of y. we have m plus 1 terms of x. And this would be our difference equation where x is the input and y is the output. Now, let's start with this equation here, and let's take the z transform of this equation. So y of n becomes y of z. We multiply it by a constant in time, and we know that multiplying by a constant in time is multiplying by a constant in the z transform, since the z transform is a linear transformation. A summation in time is a summation in the z transform. Again, we have a multiplication by a constant. But here we have a shift. So if y of n has transformed y of z, what is the z transform of y of n minus 1? Well, we know this from the properties of the z transform, right? A shift by 1 is just a multiplication by z to the minus 1 in the z domain. And so y of n minus 1 turns into z minus 1 y of z in the z transform. And we do that for each of our terms. Here it's shifted by n, so we multiply by z to the minus n. And this would be the left-hand side of the equation. We do the same thing for the right-hand side, multiplying by constants. X of n becomes x of z, and we have shifted values of x, so we have multiplications by z to the minus some power. And we get this equation in the z transform domain. Now, all of the terms here are in terms of y of z. On the other side, all the terms have at least one x of z. So we factor out y of z, we factor out x of z, and then if we solve for y of z over x of z, we get this here. Now we know from what we originally talked about at the beginning of this video, we know that y of z is equal to x of z times h of z. In other words, h is y over x. So if we come down here and say, oh, h is simply y over x, so this is going to be our transfer function. And so if we have a difference equation, we can go directly to the transfer function. For example, let's start out with this simple difference equation. By inspection, right, we only have one term of y, and the coefficient is 1, so the denominator is going to be 1. The numerator are going to be the coefficients of the x, 1 and minus 0.8, right, as we saw here. The numerator are the coefficients of the x's, the denominator are the coefficients of the y's. So this would be our transfer function for this difference equation. Now, for this one down here, again, pause the video, find the transfer function, and then let's go on. In this case, the coefficients of the y's are 1 and minus 0.2, so it would be 1 minus 0.2 z to the minus 1. And the coefficients of the x's are 1, and here we have plus 0.1 and a shift of 1. So in other words, we can go directly from our difference equation to a transfer function. We could also go in the other direction. If we knew the transfer function, we could go directly to a difference equation also. Notice that in each of these cases, I have put a question mark next to the region of convergence. It turns out that the difference equation, we can get h of z, but we can't get the region of convergence without more information. Generally, people assume that the system is causal, and if it's causal, then we could determine the region of convergence. But if we don't assume that, we can't find the region of convergence yet, and so that's why I'm leaving it unknown for the moment. We'll talk about what stability and causality mean in future videos.